let's go ahead and turn to page 8, and we're going to talk about electron configurations. And before we take the notes, what we're going to do is we're going to look at page 9 as well, and we're going to talk about how electrons fill the orbitals around the nucleus. And if you remember from your notes, there's 4 types of orbitals. We have s orbitals, we have p orbitals, we have d orbitals, and then we have f orbitals. And those are the 4 types of orbitals. Now, as we go through this, I'm going to model a lot of how you need to write these electron configurations. And so the way in which that I write these is me modeling for you how you are to do it. So make sure you're paying attention to how I'm doing it. Now the first thing we want to talk about is s orbitals have 1 orbital. And so we represent an orbital with this line. P orbitals have 3 orbitals. D orbitals have 5. There's a pattern here. How many do the F orbitals have? Well, it goes 1, 3, 5, and 7. And so, oh, it's 1 too many. Oh no, that's correct. All right, so s orbitals have 1 orbital, p orbitals have 3, d have 5, and f have 7. So it goes 1, 3, 5, 7. Now, when we write an orbital, when we write an electron will go into an orbital. However, 2 electrons can go into 1 orbital. So we need to keep this in mind. 2 electrons can go in 1 orbital. And the way that we represent an electron is we represent it by a half arrow. Now this happens to be an up arrow. We also represent them by a down arrow. So later on we're going to learn that that's an up spin and a down spin. So when we have the s orbitals and electrons start to fill the s orbitals, 2 electrons can go into the s orbitals. We have 1 and then we have 2. Now 2 electrons can go in the s orbitals. Now, if you look at the p orbitals, there's 3 orbitals. Now, what ends up happening is as electrons fill the p orbitals, you will have 1 electron go into each orbital. So it goes 1, 2, 3 like that. And then what ends up happening is they start to pair up after that. And go 4, 5, and 6. And so what I'm going to do is I'm going to erase this and show you the wrong way of writing it, and it is going to matter. You do not write it like this, but rather you write it like this. Now, even though the outcome is the same, the order in which you write them matters. And just trust me, you'll see in a moment why it matters. But a total of 6 electrons can go here. Now the d orbitals, again, what you're going to do is you're going to put 1 electron into each orbital before they pair up. And this will have a total of 10 electrons. And then the f orbitals again, you'll have a total of, in this situation, 14 electrons can go into the f orbital. So let's go ahead and recap. The s orbitals have 1 orbital. The p orbitals have 3 orbitals. The d orbitals have 5 orbitals. The f orbitals have 14 orbitals. I'm sorry, 7 orbitals. And so, again, 2 electrons can go in 1 orbital. So we have 2 electrons, we have 6 electrons, 10 electrons, and 14 electrons. And so this fact here is going to be important. The way that I did this is going to be important for how we learn how to do orbital notation, which we're about to learn right now. Again, I'm going to model a lot of things for you, and as we do it, it'll start to come together. Let's go ahead and take a look at this periodic table here. You'll see that this is the order in which electrons fill the orbitals around the nucleus of an atom. Notice how we sort of read this like a book. By the way, this right here is helium. So I want you to keep in mind that this is helium. Helium on the periodic table normally is over here, but again, it's part of the S block. So when we look at a periodic table like this, it will show it on the left there. So when we look at the periodic table, we read it like this, like a book. So we go this way, then we go this way, and we read it like a book. We go all the way from left to right, and then we go to the next row. And if you take a look here, this is actually the order in which electrons will fill orbitals, and I'll talk about that in a moment. Except there's one thing that I did that was not correct. And that what I did that's not correct is actually these last two rows here. The reason why it's not correct is because these here actually belong right here. So these bottom two rows are actually right in between the S block and the D block. Now, the reason why it's not there right now, the reason why it's put below, is because if you were to put those there, it would make the periodic table extremely long and it would be hard to put it on a piece of paper. And so what they do is they take this part out, put it below so that it's more compact and can fit on a piece of paper. So keep that in mind, that as we're going along, this comes down here through this row, and then we come back up through this row. So again, after the 6 S's will come the 4 F's, and then after the 4 F's come the 5 D's. So let's go ahead and talk about this element right here. This is fluorine. If we were to talk about how the electrons fill in fluorine, what they first do is they will first fill these 1 S's, all right? And then after that, they'll fill the 2 S's, and then they'll fill the 2 P's. Now, when I say 1 S, what I'm talking about is this is on the first energy level. And when I say 2S, this is on the second energy level. And when I say 2P, this is on the second energy level as well. Notice how there is not a 1P, because the first energy level does not have p orbitals. Now, let's go ahead and do a practice problem. We're now on page 8, and on page 8, here are the notes for the first part of what we're going to learn. What I will say is, once you know orbital notation, the other electron configurations are actually easier to learn, and we're going to learn a total of 3 of them. So the arrangement of electrons in atoms is known as the electron configuration, and it tells you where the electrons are. One type of electron configuration is called orbital notation. And so let's talk about what element is represented here. Well, remember how I said each arrow represents an electron? All you need to do is you need to figure out which or how many electrons there are. And if you were to count all these arrows here, you'll actually see that there's 15 arrows, which means that there's 15 electrons. And so this element happens to be phosphorus. Now, what each of those arrows represent, it represents an electron. It tells you where that electron is located. So phosphorus has, if you take a look, there's 2 electrons on the first energy level in the s orbitals. Then it has 2 electrons on the second energy level in the s orbitals. And if you take a look, it's got 6 electrons in the second energy level in the p orbitals. Now, something I want to point out is, notice the third energy level p orbitals. Notice how these orbitals are not completely filled up yet. And that's because phosphorus does not have enough electrons to fill it up. And so this order, if you take a look here, this is the order in which they fill up, right? And so phosphorus happens to be right here on the periodic table. And so if you look at phosphorus, it first fills the 1 S's, then it fills the 2 S's, then it fills the 2 P's, then the 3 S's, then the 3 P's. And so that's the order in which they fill. And so again, you read it like a book. You start at the top, you go read it to the right, and as you go down, you just keep going through until you get to the place in which you want to go. You do not go past that because phosphorus doesn't have enough electrons to go past that. Now, this is asking, well, what is the orbital notation for chlorine? So, if you take a look at the periodic table, you'll see that chlorine is right here. All right, and there's a couple ways of determining what the electron configuration is, but essentially, we're going to start with the 1s, then we're going to go to the 2s, then we're going to go to the 2p, 3s, then we will go to the 3p, and what I want to point out is, how many electrons will chlorine have in the 3p's? Well, the way you know that is you just count how many blocks over it is. And you'll see that it's 5 blocks over, goes 5 into the p block there, so it's going to have 5 electrons in the 3p's. Now what I'll say is, these particular orbitals are going to be completely filled. Any orbitals that you completely go through will be completely filled. And let me go ahead and show you what I'm talking about. What I'm talking about is this orbital will be completely filled. This will be completely filled. This will be completely filled. This will be completely filled because they have to be completely filled before you get to this one. And so one of the rules is this is the order in which you go, and these have to be filled before you can go to the next one. So let's go ahead and show you what I'm talking about. So what I'm saying is this has to be filled before you go here. And then this has to be filled before you go here. This has to be filled before you go here. So let's get started. Oxygen does have a total of 17 electrons. So we have 2 that goes here because 2 electrons can go into each orbital. 2 go here. And then remember, we go 1, 2, 3, 4, 5, 6. So again, when we are in an orbital where they have multiple orbitals, so p orbitals have multiple orbitals, you need to fill each one before you pair them up. And I know that in the end it looks like it's the same, but at some point it will matter, and just trust me. And then we have this one. And so far up to this point, this right here is a total of 12 electrons. So we have 5 more electrons. And again, we go 1, 2, 3, 4, 5. And this happens to be the orbital notation for chlorine. Notice how this is not completely filled yet because we have this little extra spot here that an electron can go, but chlorine does not have enough electrons to fill that. But notice how it has more electrons than the phosphorus does in that particular orbital, in the 3p's. And so what I want to point out again is if you take a look, this has 3 electrons in the p orbitals, this has 5 electrons in the p orbitals. And if you take a look, phosphorus is here where it's 3 electrons in, and then chlorine is there where it's 5 electrons in. So again, phosphorus has, in the end, phosphorus has 3 electrons, and look, it's 1, 2, 3 spaces in, while chlorine has 5 electrons, and it's 1, 2, 3, 4, 5 spaces in. So there is a pattern that will start to form. So let's go ahead and do some practice problems. Let's go ahead and do the orbital notation for carbon. So we're going to do the orbital notation for carbon. And if you look at your periodic table, you'll see carbon is actually right here. So again, we're going to start here. We will always start here. And we're going to go all the way to carbon. Now carbon has a total of 6 electrons, so in the end we'll have 6 electrons. And so let's go ahead and do this. So if you take a look, we start with the 1s's. How many orbitals do the s's have? They have 1 orbital. Then we have the 2s's next. So after 1s comes 2s. And again, s's have one orbital. All s orbitals have one orbital. Or each level has one s orbital. Now after the 2s's, you'll see that there's the 2p's. So we end up with the 2p's. And how many orbitals do the p orbitals have? They have a total of 3 orbitals. And so what we do is we put 3 orbitals there. Now what I'm going to do is I'm going to add this little, I'm going to add like a little divide between them. You do not need to do this, but I'm doing it for this particular one so that you can see where we need to fill first. So essentially we need to fill this first, then we fill this, and then we can start filling those. And so let's go ahead and do that. This is going to have 1, 2 electrons, 3, 4, and then when we get to the p's, we go 5, 6. Notice how it has 2 electrons in the p orbitals. Notice how carbon is 1, 2 blocks into the p block. So it's going to happen every single time. Also, notice how each electron is in its own orbital. Because again, you want to put 1 into each orbital before you pair them up. Now, let's go ahead and go on to nitrogen. We're going to do the same thing, all right? Now, nitrogen has 7 electrons. It happens to be right here. Happens to be right here instead. All right, so we're going to do the same thing, but we're going to go all the way to nitrogen. And so I'm going to go ahead and start going a little bit faster now. So this is going to be 1s. After 1s comes 2s, and then 2p. And again, we will fill this up, and then fill that one up. And then there's, at this point, you can see that nitrogen is 1, 2, 3 into the p block. So it will have 1, 2, 3 electrons in the p's, in the 2 p's. And if you count all the electrons there, that does add up to 7, which that's how many electrons nitrogen has. All right, let's go ahead and go to oxygen. Same exact thing, except oxygen is right here. So again, we go 1s, 2s, 2p. And again, the s's have 1 orbital, the p's have 3. We go 1, 2, 3, 4. And if you take a look, oxygen is 1, 2, 3, 4 into the p block. So it's 1, 2, 3, 4 into the p block. So now what I'm going to do is I'm going to skip on to the next page here because I'm going to move to cobalt because it's going to have a little bit more of a complicated orbital notation. So let's go ahead and take a look at where cobalt is. Cobalt happens to be right here on the periodic table. So again, we're going to have 1s, 2s, 2p, 3s, 3p, 4s. But notice what the d's do. Notice how this is the 4th energy level. Now again, notice what is happening with the d orbitals. You can see that the d orbitals actually go down by 1. And what I mean by that is, notice how this is in the 4th row, and so we have the 4 s's, we have the 4 p's, but the d orbitals will go down by 1. So in the 5th row, instead of having 5 d's, we'll have 4 d's, and then in the 6th row, we'll have 5 d's instead of 6 d's, and so on. And so the d orbitals go down by 1. And the reason why that is because these orbitals are actually in the 3rd energy level. But the 4th energy level s orbitals will get filled before the 3d orbitals. And so something to keep in mind is that when you get to the d block, it does go down by 1. And we'll talk more about that later. But anyways, let's go ahead and do this cobalt problem. And so we have 1s, 2s, and maybe look at this periodic table as you go. We have 2p, and remember the p's have 3 orbitals. Then we have 3s, 3p, 4s, I'm running out of space here. Then we have 3ds. And so let's go ahead and fill in these orbitals. Now we know the 1s's get filled, and then the 2s's get filled, and then the 2p's, again we go 1, 2, 3, 4, 5, 6, and then we go to the 3s's, and then the 3p's will get filled, and then the 4s's, and then if we take a look, cobalt is 1, 2, 3, 4, 5, 6, 7 into the D block. And so it's going to have 1, 2, 3, 4, 5, 6, and 7. And so that's how you do that. All right, let's go ahead and move on to standard electron configuration. Now this is different than orbital notation because what it does is it gets rid of the dashes in the arrows that are within orbital notation. And so essentially, if you take a look here, we've got our dashes and arrows here, and what it'll do is it'll get rid of that, and instead of writing that, it instead will add an exponent that tells you how many electrons are in that sub-level. And so we're going to take a look at this example problem of this in a moment, but what element is this? So let's go ahead and talk about how we can determine that. Well, there's a couple ways, all right? There's a hard way and easy way, or a long way and a short way. So let's talk about the long way first. If you take a look at this right here, this is telling us there's 2 electrons that are within that s orbital. This is telling us that there's 2 electrons in the 2s's. It's telling us that there's 6 electrons in the 2p's, and that there's 1 electron in the 3s's. And so what you can do is you can just add these up to get the total number of electrons, and then you can figure out what element it is. And so in this situation, there's 11 electrons, and for now we're saying electrons and protons are the same, so that means there's 11 protons, which means that it must be sodium. So it must be sodium because it has 11 electrons, because if you add 2 plus 2 plus 6 plus 1, you get 11. Now that's the long way, is adding up those electrons. There's actually a shorter way. And really, this is how I would do it. What you can do is, instead of adding those up, you can just look at this last part here. And it's literally like graphing. It's like looking at a graph and coordinates on a graph. This is telling us that it's in the 3rd energy level, in the S block, and it's 1 into the S block. And if you take a look, there's the 3rd energy level, this is the S block, and it's the first one into the S block. If you look at your periodic table, that happens to be sodium. Sodium is right there on your periodic table, so you can just look at that. So let's go ahead and do another practice problem like this. What if we had 3p3? So what if the ending of an electron configuration was 3p3? Well, here is the 3p's, and it's 1, 2, 3 into the 3p's. And so we end up with this right here. This is 3p3. Well, what if it was 3p5? Well, this would be 3p5, which would be chlorine. What if it ended in 4s2? Well, here are the 4 s's, and notice it's going to end in 4s2, which is this one, which happens to be calcium. All right, well, what about let's do 3d4. 3d4. Well, here are the 3d's, and it's 1, 2, 3, 4, which happens to be chromium. So this right here happens to be chromium. And so all you need to do is look at this last part right here, and you can figure out what element it's talking about. Now, what I'll say is once you have orbital notation down, which is this right here, the rest of it is really easy. You can figure out the other things. Again, what the standard electron configuration does is it gets rid of these arrows and the lines and instead replaces them with exponents. So we write 1s, but this is 1s2. Okay, then we can get rid of that, which is 2s2. And then we get rid of this, and the p orbitals can have up to 6 electrons. However, how many are in this particular, for this element, for carbon? Well, there's only 2, so it's 2p2. And that's the standard electron configuration. It's actually a lot easier than the orbital notation. All right, let's go ahead and do nitrogen. So again, we have 1s2. Okay, then we have 2s2. And then in this situation, it's 2p3. Okay, oxygen, 1s2, 2s2, and again, there's 2 electrons there. And then we have 2p4. And it's that simple. All right, let's go ahead and do this one. 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, and then we have 3d. Now the d's can go up to 10. You can have 10 electrons in the d orbitals. However, how many electrons are in the d orbitals in this situation? There's only 7, so it's 3d7. And so that is pretty straightforward. All right. Let's go ahead and do the orbital notation and standard electron configuration for tungsten. So what I want you to do is pause the video and then do the orbital notation standard electron configuration for tungsten, and then look at the answer that I'm about to put on the board. All right, so if you take a look here, I just made you do a whole bunch of work if you actually paused it and went through that. And this is going to actually lead to the next type of electron configuration, which is called noble gas configuration. And what it's going to do is it's going to take these long electron configurations and it's going to make them shorter. And so let's go ahead and figure out and learn this last type of electron configuration. So what a noble gas configuration is, it's a type of electron configuration that utilizes the fact that noble gases have their valence level fully occupied by electrons. And what it does is it helps shorten these electron configurations. And it's actually really easy to write a noble gas configuration. All you need to do is you need to write the noble gas that occurs before the element, so the most recent noble gas that occurs before the element, and then you write the electron configuration for the row that the element is in. So I'm going to show you an example of that. So first off, let's go ahead and take a look at this one right here. You'll see that that this is asking what element this is, and it's actually really easy. Again, we're going to use the short method where we look at this last part right here, the 7s1. And so if you look at the periodic table, where is 7s1? So if you look, here's 7, here's 7s, and it's 7s1. And so this happens to be francium. Now, so this happens to be francium here. Now what I'll say is it's asking what is the standard electron configuration for francium? Well, let me go ahead and write that for you. And notice how long that is. And so what the noble gas configuration does is it takes this really long electron configuration and it makes it into a shorter, more manageable electron configuration. Now what I want to show you is essentially what it does is when we write this, what we're doing is we're saying that that represents this part of the electron configuration. because what I just put in brackets there, if you take a look, is the electron configuration for radon. And so instead of having to write all of that electron configuration, what we can do is we can write radon in brackets and just continue after radon. So let's go ahead and talk about how can we now take tungsten, which is W here, and write the noble gas configuration. Well, again, it's really easy. So let's go and take a look at the periodic table. Tungsten is right here. And so what you do is you go to the noble gas that's on the row before it. All right, so this is in the 6th row, and so what you do is you go to the noble gas on the row before it, and all of these right here are noble gases. So the last column on the periodic table are the noble gases, and so what you do is you go to the one before it, which is xenon. You put the xenon in brackets, and then what you do is you write the electron configuration for everything that's in the 6th row. Because again, essentially what we're doing is we're starting right after xenon. And so again, we start right after xenon. We do everything, the electron configuration for the row that tungsten is in. And so this right here is the 6 S's. What comes after the 6 S's is the 4 F's right here. And then after the 4 F's, we have the 5 D's. And so that's what we need to include after that. And so we have 6S2, we have 4F14, and then we have 5D4. And so notice how this right here is the electron configuration for xenon. And so notice what's left over. It happens to be this. And so again, what it allows us to do is it allows us to only have to consider the electron configuration for the row that the element is in. So let's go ahead and do one more noble gas configuration. We're going to do it for cobalt. So let's go ahead and find cobalt on the periodic table. Here's cobalt. And so again, what we do is we go to the noble gas that's on the row before it, all right? And so we're going to write argon. And then what we do is we write the electron configuration for everything in the same row that cobalt is in. So we have the 4 S's, and then we have the 3 D's, and again, cobalt is 7 elements into the d orbitals, and that's what we end up with. Again, notice how this right here happens to be the electron configuration for argon. And so argon is replacing that entire part of the electron configuration, and then everything after that is what we end up writing. Go ahead and complete the rest of the practice problems, and then there's also independent practice problems. What I will say is this quantum number, we have not learned about quantum numbers yet. So if you see a problem with that, don't worry about it. Don't worry about answering those. We learn about those later. You guys have a great day. Thank you for enduring through this really long video. And also, I would end with a good joke, except for all my good ones are gone.